Today I'm going to talk to you about factors that affect the solubility of a solute in a solvent. There's a lot of different factors that have to do with, or help to determine rather, how well or if at all a particular solute will dissolve in a solvent, and if it does dissolve, these same factors can often determine how much of it will dissolve or how quickly it will dissolve. So what we're going to look at in terms of solubility, this is kind of a broad look, I guess. Generally, solubility has to do with the actual amount that can be dissolved. We're going to look at solubility a little bit more, zoomed out, and talk first about whether or not something can dissolve in a particular solvent as part of its solubility. We're also going to look at the amount or the mass of the solute that can be dissolved in a given amount of solvent. So if I have 100 grams of water, how much solute can I dissolve in it? And then lastly, the rate at which the solute will dissolve. Now, probably again, the most common way of expressing solubility is the second one of these two, as to the amount of a solute that will dissolve in the solvent. By looking at that one most, people tend to be assuming that the solute will dissolve in the solvent at all, which is okay to assume because that's often true. When we're talking about a solution, we're assuming it will actually work. So when we look at solubility, we'll talk about these three things, with the second one there being the one that you've heard about already and started to focus on, perhaps with solubility curves and the amounts of solute that can dissolve and how we express that on a solubility curve. So the various factors that can affect solubility, and you don't need to write these down immediately because we're going to go through each of these one by one. The first one is described as the nature or polarity of the solute in solvent. The second is the temperature, especially of the solvent when it's a liquid. The size of the solute's particles. Agitation, as if we're stirring, shaking, mixing in some way the mixture of solute and solvent. And finally, if there's a gas solute involved, the pressure above the solute solvent in a container can be a big factor in terms of keeping a gas dissolved. So the pressure when a gas is the solute. If it's a liquid or a solid being dissolved into another liquid, pressure has very little, if any, impact at all on the solubility. So let's look at nature of solute and solvent first. And as I said, we'll go through each of those previous ones on this list. We'll go through each of this list items individually just briefly. The nature of the solvent and the solute comes first because frankly, if the nature or the polarity of the solute and solvent doesn't work, the rest of them really aren't a factor at all, because if you can't get something to dissolve, it doesn't matter how much you shake it or stir it or heat it or put pressure on it, it just won't work. So whether or not a solute will dissolve in a particular solvent is based almost entirely on the polarity of the two, the solute and the solvent. Polarity, if you think back to when we talked about bonding and the polar covalent bonds, for example, that we find in water that make water molecules very polar, in addition to their geometry, that polarity, or having a pole, a positive and negative sort of pole to the molecule, can have a big impact on whether or not something dissolves. If I'm polar and you're polar, as a solution, we're more likely to try to get together into a solution and actually work, actually dissolve. But if you're non-polar and I'm polar, perhaps the solution is not as possible. So if the polarity matches, they're more likely to form a solution. More likely is important there, not guaranteed. There are lots of matched solute-solvent polarities that won't make a solution happen at all. If the polarity doesn't match, a solution is very unlikely. Again, no guarantee that it can't happen, but it's pretty unlikely when polarity doesn't match. Now, it's not a black and white here. With polarity, you can be more polar or less polar, slightly polar, very, very non-polar. And so there's lots and lots of different sort of gradations there, many different stops between I can dissolve and I absolutely can't. There are some I can dissolve a little bit, or I dissolve very slowly or slightly. So the summarization of that comes in a phrase that goes like this: like dissolves like. Like dissolves like. Now, a better way to think about that, I think, is to say it as A dissolves A and B dissolves B, but A doesn't dissolve B and B doesn't dissolve A. So if I'm like you in polarity, then a solution is more possible. If I'm unlike you or dislike doesn't work. If I'm unlike you or not like you, then a solution is less possible. So this little chart sort of does that for you. If the solute is polar or nonpolar, if the solvent is polar or nonpolar. And here are the four different combinations then. So if a solute is polar and the solvent is polar, a solution is very likely. This is the case with basically everything that you dissolve into water that's an ionic compound. Ionic compounds are quite polar. They have cations and anions that are positive and negative, and water is very polar. So when you put those together, they tend to make a good solution. Water can't dissolve every ionic compound, but it can dissolve many of them because of this polarity match. But if I take a polar solute and a non-polar solvent and try to dissolve it, it's not going to work. So take a polar solute, like say sodium chloride, and try to dissolve it in a non-polar solvent, like say hexane or something. Something very, very non-polar. Hexane's very non-polar. It won't work. Salt won't dissolve into things like that because they don't match up. And the solvent can't pull that solute apart and dissociate it into the solution. Likewise, if we take a non-polar solute, like say iodine, and put it into a polar solvent like water, it's not very likely to form a solution. Water can dissolve iodine a little bit, but not nearly as well as something that's non-polar or slightly more non-polar, like say ethanol, which has polar and non-polar characteristics to it. Finally, as you would predict, if you take a non-polar solute and a non-polar solvent and put them together, it's more likely that a solution can work. This is a good example of this would be something like using paint thinner to, say, dissolve grease off of something or to dissolve an oil-based paint. Both have a very non-polar chemistry to them, and you can dissolve oil-based paint or lacquer or something with a paint thinner where you couldn't do that with water. So that's the idea of like dissolves like. It needs to match up in order for the solution to be more likely. Not guaranteed, but much more likely. Typically, when two liquids have similar polarity, like say water, which is very polar, and let's maybe say ethanol or methanol, which is pretty polar, not as polar as water, they can dissolve together into all proportions. So we can put liquids together, and they tend to just mix and not separate. If they are able to combine, we say that those liquids are miscible, M-I-S-C-I-B-L-E, miscible. Miscible liquids, for example, water and ethanol, which is slightly polar, pretty polar. One end of an ethanol molecule is polar, where the alcohol group tends to be a little bit more polar, and can form those hydrogen bonds and things that make water polar and able to pull things apart and stick to itself as well. If two liquids don't combine, we typically would expect them to have opposite polarities and say that those two liquids are immiscible. For example, oil and water, as the old phrase goes, as different as oil and water, where their polarities are incredibly different, and so they don't go together very well at all. We would say oil and water are immiscible, and they don't mix together at all, and they separate from each other. So this is a couple terms that are sort of opposites that are used to describe specifically how liquids go together into each other to form solutions. And there are lots of liquid solutions that we use in everyday life, everything from peroxide to, say, rubbing alcohol to all kinds of things that are common to you. It's something as simple as vinegar. Oil and water, again, are classic immiscible examples. If you've talked about and heard about already in class or otherwise the term tincture, a tincture has to do with this polarity idea. Tincture of iodine, for example, is a very common one in medicinal practices. It used to be more popular in, say, household disinfection than it is now, perhaps. But iodine is dissolved first into alcohol, which is a somewhat non-polar solvent, able to dissolve iodine anyway, and then it can be mixed with water to make the solution come up to a larger volume and be less concentrated. Well, iodine can pull the ethanol can pull the iodine molecules apart and dissolve it, and then water can grab onto the ethanol essentially and sort of separate those ethanol molecules into the solution of water. And so there's a bit of a kind of combination here of solutions that are going on. You can see in the picture here that this person's having the inside of their elbow scrubbed with iodine solution in order to disinfect the skin surface before, say, giving blood or having blood sample taken. And this brings in like dissolves like in a couple different ways. I'm not going to answer the question that's given here on the screen. I'll let you think about it a little bit and try to put an answer down in your notes. How does this process of forming a solution as a tincture in this example involve the idea of like dissolves like? The second factor that we'll talk about, and a rather simple one really, is agitation. When we shake or stir or mix a solution as it's dissolving, the solute particles dissolve more quickly, and it's because you're sort of bringing in the fresh solvent, almost like you're bringing in reinforcements for the solution to form more quickly. As the solvent molecules grab onto a solute, dissociate that solute, and potentially then solvate it or surround those solute particles, the solvent molecules sort of get busy. They get occupied, and so they're not able to grab onto more. It's easier to dissolve the solution more quickly then if you get them out of the way and bring in fresh supply. And so the water molecules that have already dissolved the solute, they can't dissolve more. They have to get out of the way and let others come in and try to dissolve the rest. So it's sort of like having an assembly line or sort of like a buffet line where you have the solvent molecules sort of rotating past all the solute, and as the solvent comes past, it can kind of pick up pieces of the solute and carry them off into the solution and let the next solvent molecules come in behind. So by stirring and shaking and mixing, you're bringing in fresh solvent rather than having the same old solvent sit there next to your crystals. The best way to think about it is if you're trying to make a big pitcher of Kool-Aid, if you pour a big scoop of Kool-Aid powder into the bottom of the pitcher and don't stir, it won't dissolve very quickly. In fact, you might be surprised how long it takes it to dissolve if you don't stir it. But if you get in there with a spoon and start to stir, the whole pitcher's been dissolved and the Kool-Aid's ready to drink in a matter of just seconds because you've been mixing it and agitating it. You haven't heated it, you haven't ground up the solid, you haven't done anything else, just stirring it, and that makes a big difference. Now this can only really affect the rate of solution. Okay? This does not affect the amount of solute that's been dissolved, but the speed with which it will dissolve. You won't dissolve more by stirring, you'll just dissolve it more quickly. And sometimes it's hard to tell which is which because by stirring it, it went so fast you think you dissolved more, when in fact it just sped up the rate. This works also with gas solutes. When you stir, when you mix froth, for example, a liquid with a gas, the dissolving happens more quickly. And this is why we stir or cycle water through, bubble gases through an aquarium, for example, or if you think about how much oxygen can get dissolved into a mountain stream as that water tumbles over rocks, it's stirring the water of a mountain stream with the oxygen in the air above the stream. It's like you're stirring up that mixture, and that water is more able to grab onto oxygen molecules, dissolve them, and then give them to the big fish that are living in that river. Whereas a slow-moving or stagnant river doesn't have much dissolved oxygen in it, perhaps at all, partly because it's not being stirred up. Water treatment plants use this process when they're trying to treat water to make it usable again or releasable into the river again. One of the things they have to do is sort of spray water or stir it, agitate it over a surface that has microbes living on it that are able to digest pollutants and certain chemicals out of the water. It happens a lot faster because they sort of cascade that water or stir that water over the surface of these microbes living on kind of a honeycomb matrix or sort of a honeycomb mesh. So they're sort of simulating at the water treatment plant the natural processes that happen in nature. Water cleans itself to some degree in nature if we don't pollute it too badly. And so we can take that process and do it on a large scale at a water treatment plant simply by stirring the water as it goes over these surfaces. You increase the contact, you increase the dissolving, and you take the action to the process and put it into fast forward, essentially. The next factor is particle size. Particle size has to do with grinding up a solute in order to give it smaller pieces and increase the total surface area of the solute rather than having just a few large pieces. This is sometimes misunderstood because we would think that large pieces have more surface area than a small piece does, and that's true. But a large piece has far less surface area than many, many small pieces made from that chunk. And I'll show you a diagram that helps you understand this better if you're not sure. So what we want to do is increase that interface where the solute and the solvent can interact with each other and where the dissolving can happen. It gives the solvent more places for the solute to grab on, or rather the solvent to grab on and dissociate it. This is why you would take, say, a piece and grind it into a powder so that there's more surface area. I always think about my father-in-law who will take a huge bale of hay out to his cattle, and instead of just dropping a bale of hay in the middle of a field and letting like 6 cows be able to get their heads on it at once, he'll take that hay bale, drop it down, and then grab onto it with a scoop and spread it out across a large area. He's increasing the surface area on that amount of hay, and it gives those cows more places to come up and grab onto it with their mouths and get a bite to eat, so he can feed a lot more cows at once with that same one bale of hay. He's just increasing surface area, and there's not dissolving going on there. A little bit different process, but the same kind of idea of an interface happening there. Again, this doesn't necessarily affect the amount that will dissolve, but the rate with which it dissolves. It dissolves faster, not more, but faster. And if you look at this cube, you can see that the large cube on the top is 1 centimeter on each edge. That would give us a total surface area of 6 square centimeters on that cube. If we cut that into 8 pieces, we've doubled the surface area. If we cut those each into 8 pieces, we've doubled the surface area again. And so you can imagine taking a cube that size and grinding it into a fine powder or dust. You would take the surface area and double it many, many times over to where you'd have a surface area perhaps thousands or even more than that times more than the original surface area would have been. So the total surface area increases as the finer and finer particles are formed. One good application you can think of for this We do dissolve our drinks from powders, typically like Kool-Aid. We don't use a big block of Kool-Aid powder. We use a fine powder, so it's faster. On the flip side, perhaps you want a pill you take that you want a headache medicine to last longer. You don't take a powdered pill, you take a whole pill, and it dissolves more slowly into your bloodstream and is absorbed more slowly into your bloodstream. It's a little more complicated than that with drugs like a Tylenol or something, but you kind of get the idea. And solubility curves are often shown, used as you talk about in examples in the last video, to show the variations that happen with temperature, which is our final factor. And so solubility curves that explain that or display that for us can show the relationship between temperature on your x-axis and solubility on your y-axis. So temperature is our final factor. Temperature increases the rate at which, and the amount of which, most importantly, most solid solutes will dissolve. Solids dissolve better in warmer solvents most of the time than they do in, say, colder solvents. This makes sense. If we want to dissolve more sugar into water, we'd heat the water up, for example. Most solids do dissolve better. And you can think about it a little bit like melting. It's not melting, obviously, but it takes energy to pull particles apart when you melt them and give them enough energy to break loose from each other in the melting process. It takes energy to dissolve most solutes as well because you're pulling them apart too. Again, it's not at all the same science, melting and dissolving, but a similar idea that will at least help you remember it in your head, that solutes do dissolve better into solids into solutions when they're heated up first. And on the flip side, gases tend to dissolve better when you cool the solvent rather than keeping it hot. And on this chart, the dashed lines represent the gases. They're dissolving better, you can see, in colder water. Think about this like condensing a liquid, condensing a gas into a liquid. When you cool it, it'll condense a lot better. If you warm it, it'll stay evaporated and it won't dissolve into the solution. The final factor that has an effect on how well a solute dissolves in a solvent is the pressure. Now, pressure affects a solution's formation only when a gas solute is in play. So when you're dissolving, say, salt or sugar into water, for example, the pressure on the solution has very little effect, if any, on how well that will dissolve. But when a gas like carbon dioxide, oxygen, or any other gas is trying to dissolve into, say, water or another solvent, then the pressure can have a big impact. Basically, the idea is that the more pressure is placed above the solution, on the solvent, on the solution, the gas solute will dissolve better and in greater amounts more quickly as well. This is known as Henry's law, so that when the pressure above a solution is increased, the amount of solute that is dissolved in the solution will be greater. It's sort of as though the gas pressure above the solution is forcing the gas in the solution and keeping it in the solution, keeping it from escaping. So if you can imagine when you're a little kid swimming around a pool with a little brother or cousin or a neighbor or something, and you come up behind and sort of dunk them under the pool, as soon as you stop pushing them down, they pop right up, usually in a panic or very mad at you and looking for revenge. But the idea that if you push a gas into solution, as soon as you release the pressure, keeping it in solution, it will want to escape too. And Henry's law, it can be calculated to determine how the pressure on a solution will impact the amount of solute dissolved. We won't do any math with Henry's law, but that's the law that governs this relationship between pressure and solubility. Solid solutes, as I mentioned, are not affected by pressure. So you can witness this sort of thing every time you open a bottle of pop, whether it's a 20-ounce bottle or a 2-liter bottle or whatever it might be. This diagram sort of shows a 2-liter bottle of orange soda. And so there's an equilibrium here on the left side picture where the gas pressure is pushing down with the green arrows, and the gas pressure, or this dissolved gas pressure in the solution, is pushing up with green arrows. And they're kind of in equilibrium here. You can see they're equal to each other. But as soon as you open the bottle, you release the pressure above the solution, the top. In this gas phase, the gas escapes out the top of the bottle, and the pressure decreases very quickly. That's why when you do that, you hear not only the ch of the gas escaping through the open top of the pop, but you'll also notice the bubbles begin to immediately come out of the solution. The gas that was in that open space above your pop has escaped, and now more gas, in this case carbon dioxide dissolved in the pop, wants to take its place. So as soon as you make room for more carbon dioxide to fill that space, it'll come out of the solution of the soda to do just that. So you'll see the bubbles coming out until you screw the top back on again, and the bubbles can sort of come back to a new equilibrium again. But every time you open the pop, you release that much more carbon dioxide, and more of it has to come out of the solution to take that one's place. After a while, as you know, Any pop, if you open it a few times, after a while or leave it open for a while, it'll go flat because there isn't any more dissolved gas in the solution. Carbon dioxide dissolves very well in water, but only if we keep the pressure on it will it last like that. So when that dissolved gas comes out of the solution, because the pressure has been reduced, the solution, the concentration of that solution decreases. So greater pressure means greater solubility, less pressure means lower solubility, and eventually a flat soda too. You've seen perhaps these little screw-on devices you can get and then pump up the top of your pop bottle in order to keep the pressure on it. That doesn't really, chemically, that doesn't work. The rules of science say that sort of more of a gimmick than it is an actual functional device, because in order for that to actually keep the carbon dioxide, the fizz, in your soda, you'd actually have to be not only pushing pressure into the pop, but adding carbon dioxide pressure into that space above the soda. So it doesn't work to just simply pump in air, as air is not that much carbon dioxide. Some of you might own a soda stream machine or some other such homemade pop making devices. They inject and dissolve under pressure carbon dioxide gas. And you have to have it tightly screwed on the top in order for that fizz to remain in the solution and for it to carbonate the drink at all. So you're actually using Henry's law and a solubility rule and factor whenever you make your own pop at home. That's our final factor. Hopefully you got caught up with the notes then on all 5 of those, and we can talk about them more in class and apply them to our past labs as well as the future labs as well. Thanks for listening, and we'll see you next time.